All right, so today we are going to pick up where we left off with talking about the zeros of functions and how that relates to the degree of a polynomial. So yesterday we found a relationship between that degree and how many zeros it can have. We found that the degree tells us how many zeros we can have. So for example, we focused a lot on third degree polynomials. So a third degree polynomial, we said it could have at most 3 zeros. And then we also looked a lot at quadratics, and we found that a quadratic could have a maximum of 2 zeros. We also looked at linear equations briefly, and we found that a linear equation could have at most 1 zero. So then today what we want to do is we want to think about higher degree polynomials. So for example, what if we have a 6th degree polynomial? What if we have a 5th degree, a 4th degree? And then we can even kind of think about a 0 degree polynomial, which is a polynomial that has an x to the 0 is what that would look like, which is just a constant. Anything to the 0 equals 1. So if we follow the pattern, a 6th degree polynomial would be able to have a maximum of 6 zeros. Same thing for a 5th degree polynomial. So a 5th degree polynomial could have 5 zeros. And then a 4th degree polynomial could have 4 zeros, and a 0 degree could have 0. So a 0 degree, there are certain special cases, so if you want to, you can make a note to yourself that there are special cases that exist. There are special cases that exist, but in general, it can have 0 zeros. Okay, so let's go ahead and fill out this table together on how many real distinct zeros different degree polynomials can have. Okay, so we already did the work for 3rd degree, 2nd degree, and 1st degree polynomials. So a 1st degree can have 1 zero, and that's it. A 2nd degree, we said it could have 0, 1, or 2. A 3rd degree, we said it could have 1, 2, or 3. And I could show that to you visually. So we could look at the case of a 3rd degree polynomial again. So just a refresher. If I have a 3rd degree polynomial, this is kind of the general shape. I see that we only have 1 zero, so that's an option. It could look like this, and we could have 1, 2 zeros. Or I could switch it up again, and I see we have 1, 2, 3. Because of the end behavior, it is impossible for me to have a cubic function and not have any zeros. Because I have one side going off to negative infinity and one side going off to infinity. That means at some point we have to cross this x-axis. So that's going to be true actually for any odd polynomial. I can never have 0 zeros for an odd degree polynomial. So the same thing goes for my 5th degree polynomial. Now I do know that for 4th degree, based on the pattern, the maximum number of zeros should be 4. And then I could have any number less than that. If we look at a graph of a quadratic, we talked about how we could have 0 zeros. So right here, we never have our function crossing the x-axis. So our function never crosses the x-axis. It could touch it once and go back away, or it could touch it twice. So when I have any even degree polynomial, so if it has a degree 2, 4, 6, 8, the end behavior is going to be the same in both directions. So it's either going to be pointing up both directions, or we could have had quadratic that's pointing down and going to negative infinity in both directions. So what this ends up doing for us is any odd degree polynomial can have at most that same number of zeros and cannot have 0. And then for even, it can be 0 all the way up to whatever degree it is. So a 6th degree can have up to 6 zeros, including 0 zeros as an option. So this is what our table should look like. And now, yesterday we talked about how algebraically we can solve for these zeros. So yesterday we talked about how we can find the zeros of a function. We can find the zeros of a function by setting that function equal to 0 and then solving for x. So that's our strategy to algebraically solve for these zeros. And we talked about how we can factor a function in order to do that. So let's take a look real quick at this function here. So suppose we want a 6th degree polynomial that has 6 distinct zeros. Well, I know that a 6th degree polynomial has an x to the 6th power in it. That's what makes it in a 6th degree polynomial. So I know that if I have a degree 6 polynomial, I have some x to the 6th power, I could factor that out into potentially 6 different groups. So here in that very first line, I have p of x equals x times x plus 1 times x minus 1 times x plus 2 times x minus 2 times x minus 3. So those are 6 different groups. So if I were to distribute, and it would be a really long problem, like to do all of that distribution, but in the end, I would have an x multiplying, x is multiplying together until we have x to the 6th power, because there are 6 x's there, and they're all going to end up being multiplied together. So I would get x to the 6th power, which is exactly my 6th degree polynomial. So when it asks me to construct a polynomial with 6 different linear factors, here's a couple of examples. All we have to do is recognize that if we want a 6th degree polynomial, I can just break it up into 6 different groups with x in it. So 1, 2, 3, 4, 5, 6. Because if I have x in here in each of these, and I need 6 x's total because it's 6th degree, if I set this equal to 0, I know that if any of these groups equals 0, if any of these groups is 0, then the whole thing is 0. So it's letting me be creative. I could choose whatever I want in here. X plus 1, x minus 1, x plus 45, x, I don't know, minus 100, minus 2, plus 4. So you could come up with a different equation for me, and that's okay. We would still both have 6th degree polynomials with 6 different zeros. And they're going to be different as long as I don't have any repeated. Now, question 3 here. So question 3 is asking us to construct a 6th degree polynomial with exactly 3 distinct zeros. So the equation that we just wrote here, this has 6 unique zeros. So if I were to solve this, I would get x equals -1, x equals 1, x equals -45, x equals 100, x equals 2, and x equals -4. So all of those would be zeros. So all I did here was I set x plus 1 equal to 0 and solve for x. Set x minus 1 equal to 0, x equals 1. So I solved each of these for 0. I set them equal to 0 and solve for x, because if any one of these is 0, that makes the whole thing 0. So all of these x values are solutions. So I need all 6 of them. All 6 of these possibilities would make the whole thing 0. Now we want to come up with one. Now we want to come up with one with 3 distinct zeros, 3 unique zeros. So let's come up with a 6th degree polynomial with 3 unique zeros. All right, well, it's still a 6th degree, so I know that I need to have 6 x's. But I only want 3 unique ones. So I know I only want 3 groups. I only want 3 groups because I only have 3 unique zeros. So what I could do is maybe I square each group. So maybe this group is repeated twice, this group is repeated twice, and this group is repeated twice. Because if I set this equal to 0, if any one of these 3 groups equals 0, then the whole thing equals 0. So let me go ahead and fill in values. So maybe I have x plus 1, x minus 4, and x plus 8. Maybe that's what I chose. Again, you can get creative. Then whenever x plus 1 equals 0, the whole thing equals 0. So when x plus 1 equals 0, the whole thing equals 0. So that means when x equals -1, that makes my whole function 0. Now, since this is squared though, that means I have this 0 twice, which means I no longer have 2 distinct zeros coming from this one. It's going to be the same one twice. So if I had written out my polynomial, written this out expanded, this is the same thing as x plus 1 times x plus 1 times x minus 4 times x minus 4 times x plus 8 times x plus 8. So writing like this might be more helpful to you, and that's totally cool. So that's just me expanding what I wrote here, but you could have done this as a first step. You could have said, okay, well, I know I need 6 x's, so I'm going to have 1, 2, 3, 4, 5, 6. But I only want 3 unique zeros, so I'm going to repeat them so that some of them are the same. Some of them are repeats. So this one and this one is the same. This is only going to give me 1 distinct 0. This one and this one is the same, so I'm only going to get 1 distinct 0 and 1 here as well. So x equals -1, x equals +4, x equals -8. Let's go ahead and try to come up with another one that has exactly, let's try it for 4. Let's do 4 distinct zeros. So let's write a 6th degree polynomial with 4 unique zeros. All right, well, if it's the 6th degree, then I'm going to split it up into six groups with x in it. Because I know if I multiply x's together 6 times, that gives me an x to the 6th power, which is what I need to have a 6th degree polynomial. Oh, I need one more. All right, and then I can choose what I want to fill in, but I need to fill it in such a way, that I only have 4 unique zeros. So right now I have 6 groups, but I only want 4 of them to be unique. So maybe for the first one, I say, okay, maybe I'll have x plus 1, x minus 1, x plus 2, x minus 2. At this point, I have 4 unique zeros. These are 4 unique groups, so they'll give me 4 different x values that give me 0. So that means for my last 2 groups, I need to repeat somehow. So I can choose which ones I want to repeat. So maybe I'll repeat the x plus 1, and maybe I'll repeat the x minus 2. So this is coming up with a 6th degree polynomial that has 4 unique zeros. I only have 4 unique groups being multiplied together. So I know that if I were to solve these for their zeros, I would get x equals -1, x equals +1, x equals -2, x equals +2, x equals -1, and x equals +2. So here's a unique zero. Here's a unique zero. I have it twice, so I only get to count it once. X equals 1 is unique. It's all by itself. X equals -2 is unique. And then x equals 2 is repeated. So I only have 1 unique out of that. I only have x equals 2. I would only really count it once, because after that it's repeated. So that would be a 6th degree polynomial with 4 distinct zeros. So this would be my solution. This would be my answer right here. And you do not have to actually multiply this function out. So I could quite literally just write f of x equals those 6 groups multiplied together. And I constructed it in such a way that I only have 4 unique zeros. All right, so let's do a couple of problems where we solve to find the x-intercepts. So first it asks us to identify the maximum number of zeros it can have and then to actually find them. So earlier we discussed that the pattern is the degree tells me how many zeros I can have. So if this is a 3rd degree polynomial, I can have a max of 3 zeros. Now I want to find what those zeros are. So what I do is I set my function equal to 0 and I'm going to solve for x. So I'm going to set this equal to 0, so x cubed plus x. I want to know, when does that equal 0? What x values give me 0? Well, I can factor out an x, and I get x squared plus 1. Now I can't solve any further from here, or I can't factor any further from here, I should say. But I know when x equals 0, that the whole thing will be 0. And I know that when x squared plus 1 equals 0, the whole thing equals 0. So I can go ahead and keep solving for x. X squared equals -1. X equals plus or minus the square root of -1. All right, so here we ran into another square root of a negative number, which for now we cannot have. In a little bit we'll talk about it, but this is not a real number, so we're just going to cross it out. This is my only real 0. So when x equals 0, y also equals 0. So that is my function 0. This would be my solution, x equals 0. We can do the same thing here for the second one. If I were to expand this out, I would have g of x equals x plus 1 times x minus 1 times x minus 1. So whenever I see something squared, so like right here, I saw that this was squared, I'm going to go ahead and square that whole group because the square is on that whole group. So that's saying that I have x minus 1 times x minus 1. So now if I look at my function, if I multiply 3 x's together, I would get an x cubed. So I know this is going to be a third degree polynomial. This is a third degree. This is a third degree polynomial, which tells me I can have a maximum of 3 zeros. All right, and I can solve for what those zeros are by setting the function equal to 0. So I'm going to set the function equal to 0. So x plus 1 times x minus 1 times x minus 1 equals 0. Well, I know that if this group here equals 0, then the whole function will multiply to equal 0. I'm going to go ahead and solve for x. I subtract 1 on both sides. So that is my first solution. For my second group, if x minus 1 equals 0, then the whole thing equals 0. So x minus 1 equals 0, I'll add 1 on both sides and end up with x equals 1. And then for my last group, if x minus 1 equals 0, then the whole thing equals 0. Add 1 to both sides, I get x equals 1. But that's a repeat, right? Which we might have already recognized by the fact that it was squared. So I only have 2 unique zeros, and they are x equals -1 and x equals 1. So we could include it if we want to, but it's not really necessary since it is a repeated value. Okay. So if you want to try the next two for practice, you can, and we'll talk more about factoring. So if you have to kind of look up how you could factor this out, that is okay. Here in number 5, what we're going to do is we're going to construct fourth degree polynomials with the following characteristics. So in the very first one, we want a fourth degree polynomial with exactly 4 distinct real zeros. So if I want exactly 4 distinct real zeros, well, I'm going to create a function. I'm going to have f of x equal, and then I'm going to go ahead and create an outline for myself of 4 groups. 1, 2, 3, 4. All right, so exactly 4 distinct real zeros. So I know that each of these 4 groups needs to be unique. So each group needs to be unique. So I might do x plus 6 for one group. I might do x minus 3 for the next group. X minus 2 for the third group. And maybe I'll do x plus 8 for the last group. So you could choose anything. As long as you have 4 groups being multiplied together, where each group is different, then that's going to give me those 4 distinct real zeros. All right, for the next one, we want exactly 3 distinct zeros. So we're still working with this 4th degree polynomial, but now we only want 3 distinct real zeros. So my function equals, I'm going to go ahead and give myself 4 groups. It's a 4th degree polynomial, so I know I want x multiplying together 4 times to give me that power of 4. So for the first one, I might do x plus 2. For the second one, I might do x, I don't know, minus 1. For the third one, I might do x plus 10. At this point, I've already come up with 3 distinct groups, right? And I only want 3 zeros. So that means I need to repeat one of these. So I could repeat any one of these. I might just repeat the last one. I might just repeat that last one. Because this way I have 1, 2, 3 unique ones, and then one of them is a repeat, so that won't be a unique 0. If you want to, you could write this condensed down a bit, so you could have written f of x equals all of this. Copy, paste. And then you could have just squared one of the groups. That would work. Let's go ahead and look at C. So take a moment, see if you can come up with one that has exactly 2 distinct real zeros. So exactly 2, and then go ahead and try D as well. Try to come up with a 4th degree polynomial with only 1 distinct 0. And then you can try to come up with one that has no real zeros. All right, so that is where I am going to stop for this video. Let me know if you have any questions though.